the thermal processes.
Hey, everyone. So I'm really happy to be back at my favorite workshop. So huge thanks to the organizers for continuing this. Today I'll be presenting our work I did with Nelly, who's in the audience. We originally put our manuscript on archive last this year, but we were able to make some significant improvements on our result and update our manuscript just last month. So yeah, even if you've already read our paper in March, this is a good time to revisit. Oh, and I'm having this problem with my voice this week, so please excuse me even if this becomes a bit rough. Right. Okay, so I'm interested in different classes of reoperations that kind of form a hierarchy. And their common factor is that they preserve the Q state after those operations. And obviously, the biggest set of such operations is the set of Gibbs-Friedrich operations. But we are more interested in the subsets of Gibbs-Friedrich operations, namely summary operations, which we call TO, elementary summary operations, which we call ETO, and Markovian summary operations, MTO. So Camille already nicely introduced summary operations, and I believe most of the audience love summary operations. It's a very nice framework, physically motivated and everything. But why do we need to care about ETO and MTO? So, okay, I will define them properly in the next slides. Just for the motivation, they are defined with some additional restrictions on the TO. And those additional restrictions are, I would say, experimentally motivated. Some people would disagree, but so by studying these operations, we can approach a let's say more experimentally motivated or real world motivated problems. Yet they were proposed in 2018 and 2022, but I would say they haven't been studied that extensively yet. And I suspect two reasons for that. So the first reason is that they are strictly weaker than TO. And people usually want to even strengthen the TO for the reversibility and stuff like that. So that's one reason. And the second reason, and I think this is even more important reason, there exists some way to characterize the state compatibility of this ETO and MTO, but they are extremely inefficient. And for my previous project, I tried to do it with the help of my workstation in our group. And I couldn't do it over dimension 8. So yeah, that's kind of a problem. Okay. And I am claiming that we solve this problem, and this for the case of catalytic convergence. So the one-line summary of our result is that catalytic summary operation, catalytic elementary summary operation, and catalytic Markovian summary operation are equivalent. So it's quite surprising, and it's honestly quite a daunting statement, especially considering that characterization for 8-dimensional ETO is practically impossible. But once you get the trick, it's pretty simple and easy. All right, so Camille already did this, so I'll just quickly go through some more pages. They are the channels. They consist of 3 steps. First, you attach the Gibbs state. The temperature is fixed, but the mass Hamiltonian, you can choose anything. And then the mass of the system will evolve interiorly with this energy prism unity. And then you discard some subsystem. For my talk, I will always discard the system that we appended. So the dimensions always stay the same after the channel. So basically, we can choose any submass with a fixed ambient temperature and any energy preserving interactions as long as they preserve the energy strictly. Okay, so for ETO, our restriction is the number of levels we can manipulate at a time. So essentially, this is a channel, which is a concatenation of different TO channels, each of which act only on two nodes. In the original definition, they also allowed complex combinations of those concatenations, but for our proof, we don't need that, so we will skip that part. More formally, this is a concatenation of channels phi's, and each phi's are TO, and they are two-level channel. And what is two-level channel? They are induced by this two-level system of unit trees that leave all the energy levels unless their system energy level corresponds to the two level we choose that we care about. Right, and the last set of operations is the FTO. This is another strict subset of TO. We know that there are some ETOs that are not MTO, but it is not very evident yet if there are some MTO that is not MTO. Okay. So these are the channels that are infinitesimally divisible. So we can imagine as an evolution from 0 to t, and it has a semi-group structure. And if you slice any two times, the evolution between these two times should also be some operation. So physically speaking, we can attach any small bus to the system, and we can do any energy rhythmic interaction between the system and the bus, but the bus should always stay in equilibrium, thus Markovian. Okay, the final ingredient is the catalysis. So catalysis is a process from rho to eta, and this rho to eta is not possible without the catalyst via free operation, but with some catalyst state sigma that is recovered at the end, we can do this transformation from rho and sigma to eta and sigma by free operation. So this recovery has, different people have different notions of recovery. I will follow the nomenclature of this recent review paper. So the most conservative notion of recovery is the strict catalysis. You want the catalyst to be recovered exactly, and you don't want any correlation to the system. We can relax like one of these two restrictions. If we relax the correlation part, we want the catalyst to be recovered exactly, but we don't care about the correlation. And if we relax the exact part, we don't allow any correlation to the system at the end, but we allow some error bounded by some number. Okay. So now we have to define the set of state transformations by catalysis. So this is, we are kind of using a notation, and this is not the set of channels like TOHS beta I introduced. Because catalysis kind of depends on the initial state, and different catalyst states should be chosen for different initial state and for different tasks. So this is not a set of channels, but rather this is a set of possible state transformations with some catalyst, with some catalyst Hamiltonian, and free operation, some free operation in the setup. And we will choose the recovery condition, either strict or correlated or approximate, and we will apply those consistently over different set of operations, TO, ETO, and MTO. Okay. So actually our result is like our three results, like strict CTO equals to strict CETO equals to strict CMTO, and correlated CTO equals to correlated CTO, and so on. Okay, this is our trick. We define another set of state transformations that use Gibbs catalyst. That means we use Gibbs state with respect to the ambient temperature as our catalyst. This sounds weird, but I will explain it a bit more in the later slides. So this set, we only use, consider strict catalysis, and we can choose any catalyst Hamiltonian, but the temperature is the same as the ambient temperature. Okay, so our first result, or maybe our intermediate result for our main result, is that some operation equals to GC gives catalytic ETO equals to gives catalytic MTO. So for many of you, it should sound a bit odd to use Gibbs state as a catalyst because Gibbs state is a free state for the sum operation, and indeed for sum operation, Gibbs state does not help. So GCTO is equals to TO. However, once we have some sort of Markovianity in post-optimal operations, we found out that, well, actually, Kami also did similar work this paper that gives state catalyst might help. And so let's see what's Markovian about elementary small operations. So elementary small operations, they are a combination of different TO channels. That means we append the bus, we do the energy preserving operation, and then we trace out the bus and then continue. So this tracing out kind of imposes some sort of Markovianity because we cannot just retain the bus and use it again and again. However, each of these TO channels, they are not completely Markovian, so they have some non-Markovianity also, and that's the reason that ETO is not the same as NTO. Okay. However, if we use catalyst, this catalyst will retain its memory throughout the concatenations of these operations, and we use that memory effect to actually enhance our ETO and NTO. So our initial intuition for this version 1 paper was that we can use Trokosuchiki product. So any energy preserving unitary interaction, energy preserving unitary operator is a exponential of some interaction Hamiltonian, and any interaction Hamiltonian can be written as a summation of different two-level terms that are each of them energy preserving. And you have exponential of some, so naturally you convert it to product of exponentials with some vanishing error that is inversely proportional to the number of chopping we do. So that was our initial intuition, but this small error kind of causes some problem. So for TO and GCTO case, it was more or less okay. But once we require strict catalysis, that means we want no correlation, no error to the catalyst, even in the presence of this O1/n error. We couldn't really prove that for coherent initial states rho if CTO is a subset of CTO or not. And that's because we used some majorization for this proof. However, we found a way to circumvent this problem. So now we can really claim that GCTO is equal to TO without any error. So what we do is like we consider like a subset of some operations by fixing the mass Hamiltonian. Then you have all the energy preserving unitaries that you can do, and they actually form a compact and connected league. Now you use the same Hamiltonian as your catalyst Hamiltonian, and use the same mass as the Gibbs catalyst. Then you consider all the two-level energy preserving interaction Hamiltonians. You construct the Lie algebra with that, and then exponentially, then you get the same connected, compact and connected league. And then there's this lemma theorem in the control theory that you can generate any element of this Lie group by a finite product of exponentials of the generating set of the Lie algebra. So essentially, we can decompose any energy preserving unitary into a finite product of two system level energy preserving unitaries. And we want to recover the catalyst, but since our catalyst was a very resourceless state, which is a Gibbs state, we can just simply resolutize the catalyst, and that is not a problem for both ETO and NTO. Okay, and later we found out that there actually exists a very simple construction for this decomposing energy preserving unitary into two-level energy preserving unitary, and this we can do by just adapting like one of the subsection of this one chunk. If you're interested, please talk to me. Yeah. So finally, our main result, CTO equals to TMTO. What we do is like we consider a catalytic sum operation using some catalyst sigma c, and we get this rho as c. Now, for the ETO or MTO, we use sigma and the sum of mass as the catalyst. Then this TO process can be replaced by ETO using this additional catalyst, additional Gibbs catalyst, and we get the same state tensor, the Gibbs state. If we require like the strict catalysis condition in the beginning, we also obtain the final state that is all product form, and we recover the catalyst strictly. If we, for example, require approximate catalyst, then this final state is the final state tensor some erroneous catalyst, and for this big thing, we also have this bond. Okay, right. I will just like conclude with the outlook. So this is not my result, but last year Imam Avian talked in this result workshop about overcoming the low quality. So basically, if you have symmetric operation and if you have additional restriction, which is low quality, also experimentally motivated, you don't have the full set of symmetric operation. However, if you have one like cubic catalyst, for example, you can make this local symmetric operation equivalent to symmetric operation. And I really like that our result kind of parallels that result. If we have this two-level restriction, it is strictly different, but with the catalyst. Here we have Markovian effect that is helping bridging the two-level and the full-level thing. And here the catalyst is kind of redistributing the concept quantities. So we now know like two kind of origins of the power of the catalyst, and I'm really looking forward for other people to track what is the next, what is another origin of the catalyst. Okay, thank you.
Thank you for the very nice talk. We've got plenty of time for questions. Yeah.
Thanks, that's really interesting. So you mentioned that MTO is not, like, it's not known whether there's something in MTO that's not ETO, but didn't come as in Mateo.
Yeah, that's true for state convergence for incoherent input states. In that case, any MTO transition can be decomposed into ETO transition. But I just don't know if that's also true for coherent input.
Further questions? I was wondering whether you have any relation on the following thing. Like if you restrict the catalysts to be very small in dimension. So for example, like qubit catalyst, so a single qubit for MTO, for ETO, would you expect that this collapse would still happen, or you preserve, so you still have gaps between these classes of operations?
I think I actually have a slide for that. So yeah, so okay, this is for a very specific protocol, and your system state is three-dimensional, and I vary the dimension of the catalyst. So one dimensional catalyst is like no catalyst, right? So you start from ETO here, and this is the TO limit. And blue lines are kind of like the optimized catalyst, and red lines are the worst catalyst in some sense. And this is actually the Gibbs state catalyst. And you can see some sort of convergence. Yeah.
One of the goals of like ETO was to be able to do some interesting operations like an NMR device or something. So I'm wondering if this allows for some more easier implementation of any kind of
You mean like ETO itself? Yeah, so ETO is basically global by a series of interaction between two levels and the resonant harmonic oscillator with some intensity dependent chase comics interaction. And I'm actually not very sure like what kind of physical platforms have this intensity dependent chase comics operation interaction as a natural interaction. I heard that some superconducting platforms have those kind of native interaction. Not sure if I answered your question. I see, I see. Yeah, I agree that like we might have something even with like smaller couplets. That's also related to Giovanni's question. But the problem is that like our proof relies on using the Gibbs bus itself as a catalyst. And then it's not very different from TO in terms of the degree of control required. So as of now, I don't have any solid example.
More questions?
I think I could maybe version 1.0 of the previous show, so it's a great upgrade. I'm curious, so when we think about this thermal operation of Gibbs state as a catalyst, it's, I suppose, generating quantum correlations as is going on with such a system. So if we had a classical catalyst, in the sense that all the quantum correlations immediately trace out at every infinitesimal amount of time, do you think that would restrict the type of operation you would have access to? So instead of a quantum catalyst, the classical incoherent catalyst. See, yeah, that's very interesting. Yeah, that's related to like what I also want to push on this direction, which is like now we are considering fully normal covariant catalyst. Maybe we can do some summarization for this going on. Yeah, maybe we can discuss. This is something we can definitely discuss. Well, thanks.
I was wondering if you had to worry about embezzlements of work in your use of catalysis.
So this result holds even for the street catalysis without any error. And I guess in that case, we don't have to worry about embezzlement.
Questions? But let's take it to the coffee break. Thank you very much to